So whenever we do have PCB designing, we do have lots of issues. Okay, issues related to designing of dimensions of PCB tracks, deciding the widths and lengths of the component leads. Okay, deciding voltage and current specifications, deciding the thickness of your PCB clad. Okay, usually that is ferrite core or polymer material, deciding whether you want to go with a multi-layer PCB. Okay, 50, 60 or 2 or 3 depending upon complexity of your design. But do remember that whenever we do have PCB design for digital circuits which are operating in the range of megahertz, they do have a clock running through the PCB tracks. Okay, so megahertz is a very huge frequency, and that is going to create electromagnetic interference in the tracks. Particularly your clock track is the highest switching track, current switching track, because 101010 continuous होते रहता है. It is the highest switching track on your PCB, and it is more responsible to generate EMI, electromagnetic interference, for other tracks which maybe are switching on the lower rate compared to the clock signal. Okay, so our design has to be electromagnetic compatible. Okay, we know that EMI is going to be there for sure. We cannot avoid it, we cannot remove it. It is going to be there forever. We have to take care of it, we have to reduce its effect. It is called as our instrument product or design is electromagnetic compatible, and the ITC have lots of norms and rules for having the EMC design so that we can reduce the effect of EMI. So here is an example for circuit board layout for EMC. Okay, I will share that example with you. This is a 14-minute video. I will turn on the captions as well. Please be with the video. It may happen that you may lose the context with this video and another video which we are going to see after completion of this example. Okay, let us go through the video.
This example is brought to you by Learn EMC. Here's an example.
Are you able to listen the audio? Hear the audio?
Yes, sir, clearly.
Okay, great.
This example is brought to you by Learn EMC. Here's an example of a printed circuit board that's likely to fail radiated emissions requirements. In this video, we'll show you how to change the layout of this board so that radiated emissions requirements are easily met. We'll also make some changes that improve signal integrity on the board. Before we get into the specific problems with this layout, let's take a closer look at a few relevant details of the design. From the circuit board layer stack up, we see that we have a 4-layer board with both power and ground planes. Notice that there's 1 millimeter of spacing between the power and ground planes. Power planes spaced greater than 0.5 millimeter are considered widely spaced. The black dots on the board represent vias connecting to the power plane, and the open dots are connections to the ground plane. There are 4 decoupling capacitors connected between the power and ground planes. This is considered global decoupling since these capacitors are not located close enough to the active devices to be considered local. Notice that the board has 3 external connectors: a 6-volt power input, an acoustic signal input, and a digitized signal output. This is a mixed signal board since it has both analog and digital circuits. Now, with respect to unintended radiation and signal integrity, there are two major problems with this board and also a few minor problems. The first major problem is that high-speed circuitry is located between the external connectors on the board. This can cause cables attached to the connectors to radiate at unacceptable levels. The second major problem is that the decoupling is inadequate for this particular board. Poor decoupling can lead to voltage fluctuations between the power and ground planes as the various devices demand current. In addition to these two major problems, the I/O lines bring signals too far onto the board, and other digital lines, such as the clock lines, are also longer than necessary. To reduce interference to these signals, we need to shorten the traces as much as possible in the new layout. One final problem is that the unamplified acoustic signal shares the same ground plane return path as the digital signals. The interference resulting from sharing a return path is especially detrimental to signals that are both low frequency and low amplitude, and that's exactly what we have here with the unamplified acoustic signal. Now let's look at each of these problems in a little more detail so that we can determine a better way to lay out this board. Let's start with the problem of the placement of the high-speed circuitry between external connectors. This layout will cause a voltage difference between the connectors on opposite sides of the board. As a general guideline, if the circuitry between connectors has signals at tens of milliamps, operating at frequencies of tens of megahertz, then that will produce millivolts between external connectors. Now, the cables attached to the external connectors can behave as antenna parts, so millivolts of potential difference can cause one cable to be driven relative to another cable at a level that can easily exceed radiated emissions requirements. So what's the solution? There's only one good way to address this. We need to rearrange the board so that the high-speed digital circuitry is not located between external connectors. Now, if we just leave the connectors in place and move components around, there's really no good place to put the high-speed circuitry so that it's not between the connectors. What we need to do is move the external connectors. Let's go ahead and move the connectors to the bottom right edge of the board like this. With the connectors in this new position, we can rearrange the components on the board so that all the high-speed circuitry is toward the left side of the board. Let's go ahead and drop the traces for now and move the components to this position. Notice that some of the components have been rotated relative to their original position on the board. Also, there were 4 global decoupling capacitors on the original board, and we've just moved them out of the way for now. This arrangement of components will allow us to shorten I/O lines and other high-speed digital lines, which reduces the likelihood of interference. But most importantly, with this new arrangement, we'll be able to lay out the traces so that there's no high-speed circuitry between external connectors. This means we've addressed the first major problem associated with this board. The second major problem with the original board was poor decoupling. This can cause voltage variations between power and ground, which can affect the operation of the devices and can also cause radiation or signal integrity problems. Decoupling is intended to stabilize the voltage difference between power and ground. Now, this board already has 4 decoupling capacitors, but the original placement of these capacitors was global. Boards that don't have closely spaced power and ground planes should have local decoupling. Recall that this board has widely spaced power and ground planes since they are separated by more than ½ millimeter. When an active device on a board with widely spaced power and ground planes draws current, the current comes from the power planes first unless there is a local decoupling capacitor very close by. We need to move the existing decoupling capacitors much closer to the active devices and also add a few more. Here's a method for locating decoupling capacitors on boards with widely spaced power and ground planes. This method assumes that the active devices and decoupling capacitors are on the same side of the board, which is the case we have here. First, Look at the layer stack up to determine which plane, power, or ground is the most distant from the component layer. If the power plane is farthest from the component layer, then the decoupling capacitor should be placed at the power pins of the devices. Whereas if the ground plane is most distant from the components, the decoupling capacitor should be placed at the ground pins of the devices. For this example, the power plane is farther from the component layer than the ground plane, so we want to locate the decoupling capacitors near the power pins of the components. Recall that connections to the power plane are shown by filled dots on this layout. We'll place the decoupling capacitors so that they share the via connecting each device to the power plane. Now, if for some reason we could not place the decoupling capacitors right next to the component pin, it would be okay to place the capacitor and the via a few millimeters away. A short trace connected to the active device is fine, but decoupling capacitors should always be connected to the plane through vias adjacent to the mounting pads. So here's where we'll place the decoupling capacitors relative to the devices. Notice that the gate array has 3 power pins, so we gave it 3 decoupling capacitors. The other devices have just 1 power pin, so they each get 1 decoupling capacitor. This placement of local decoupling capacitors will significantly improve the decoupling on this board. And this takes care of the second major problem that we identified on the original layout. So now let's take a quick look at the acoustic signal return path problem. Let's go back to the original layout for a minute. The unamplified acoustic signal shares the same ground plane return path as the digital signals. Recall that current flows in loops. So the current from the acoustic signal input connector to the analog amplifier has to somehow find its way back to the connector. With this original layout, the current will be dumped onto the ground plane at the ground pin of the amplifier, and then it will make its way back to the ground pin of the connector in order to complete the loop. Now it turns out that low frequency currents that use a ground plane as a return path will spread out on the plane, taking every available path according to the impedance of the path. This spreading out of the return current makes low frequency signals particularly vulnerable to interference on the ground plane. So where does the interference come from? Signals that share the same current return path can experience crosstalk due to common impedance coupling. Typically, this crosstalk is on the order of -60 dB, or 3 orders of magnitude, although it could be greater for long traces running side by side, or it could be less for circuits that are distant from each other. Using the -60 dB estimate for the crosstalk, a digital signal at 3 volts can be expected to generate about 3 millivolts of low-frequency noise in a circuit sharing the same ground plane. A general rule of thumb is that low-frequency signals should not share the ground plane as a current return path unless -60 dB of crosstalk can be tolerated. We need to provide a separate return path for the acoustic signal by adding a dedicated trace tied directly to the amplifier ground pin. This will ensure that the current for the acoustic signal input will return on the trace rather than on the ground plane. We'll implement this extra trace in the final layout. Okay, here's our new arrangement again. We've discussed solutions for each of the problems on the original board, and we're ready to add the traces to the new layout. So let's do that now. And here's a layout that addresses all the problems we've discussed. The dashed traces indicate that we routed the 64 MHz clock on layer 4. This was not essential, just convenient. Let's look at the original board and the new layout side by side for comparison. Here's the original layout on the left and the new layout on the right. We moved all external connectors to the same edge of the board and shifted components so that the connectors are located to the right and below the high-speed digital signals. This arrangement avoids high-speed circuitry between external connectors, which prevents one connector's cable from being driven relative to another connector's cable like a dipole antenna. The new position of the components allowed us to significantly reduce the length of the I/O lines and high-speed digital lines on the board. We provided local decoupling capacitors for each active device. These capacitors share the via connecting the device to the power plane, which is the plane farthest from the component layer. This local decoupling allows each device to pull current from the closest decoupling capacitor first, rather than from the power bus. And finally, we provided a dedicated trace for the return current of the unamplified acoustic signal, tying the trace to the amplifier ground pin. This was necessary because the acoustic signal is both low amplitude and low frequency, which makes it sensitive to interference from other signals using the ground plane as a return path. This new layout should easily meet radiated emissions requirements without a shielded enclosure. A few final notes. Depending on the nature of the digitized signal output, this cable may need to be shielded. If so, the shield should be grounded to the board's ground plane. Also, depending on the specific devices used and the quality of the power input, additional bulk decoupling may be required. And finally, notice that we did not provide a separate dedicated return path for the amplified acoustic signal. The current return path for this signal is the ground plane, and since this is a low frequency signal, the return current will spread out. However, this signal has a higher amplitude than the unamplified acoustic signal. The implicit assumption we made was that the amplified acoustic signal would not be sensitive to crosstalk at -60 dB. If this is not a good assumption, a dedicated return path should be provided in the form of a trace from the ground pin of the digital analog device to the ground pin of the amplifier, with a single point connection to the ground plane. We'll see a case like this in a future example. For more information, take a look at the articles PCB layout and circuit board decoupling. These tutorials are available on the LearnEMC website.
Okay, probably you have understood that why adjusting the return path for the signals is important. Here the example taken was for the acoustic signal, that is your voice signal or audio signal. Okay, those are relatively less in frequency. So if we talk about the audio signal, those are from 20 Hz to 20 kilohertz. But if you think about the ADC or the processors which are mounted on the PCB, they work usually in the range of megahertz. So we have to put the decoupling capacitors every time, the bypass capacitors. The bypass capacitors protects the surges or current shoots in the circuit. Okay, whereas decoupling capacitors, as name it indicates, it decouples the interference. It decouples the way of interaction in between the two traces or two tracks through EMI. Okay, so capacitors are very important in PCB designing. If you look at various PCBs, you will have yellow color SMD packages. The black colors are register, the yellow colors are capacitors. Okay? Without capacitor, we cannot work. Even if you go with the microcontroller designing, the clock signal of microcontroller is always associated with the two capacitors, 0.01 microfarad. Okay, so it is very important to consider all these aspects while designing a circuit on PCB. Okay, then we do have another video which talks about the introduction to concepts in PCB designing. Okay, in some way, some another way, this discussion is related to the syllabus for us. Okay, and this will be the last video with which we are going to deal with. and in next session we are going to go through the various points of the syllabus. Okay, so we are going to see this video for next 10 minutes. The complete video is for of 25 minutes, but we are not going to go through the complete video but the chunks of the video. Okay, and this video is little bit hard to listen, so please be with the video. I have turned on the captions. You can read the captions so that you will be connected with the video. Okay, I will start the video now.
All right, we're going to introduce you guys to some basic concepts in PCB design. So for a lot of you, this will be the first time that you've ever designed a PCB. I suspect for most of you that's the case. And so there's a couple of important concepts that you'll want to kind of understand, and some sort of basic terminology that you'll need to know to be able to understand what it is that you're doing. Now, the other video that Chandan has produced will describe how to go through steps, and some of the things that he's going to take you through is to go through some of the key steps in the design process, which essentially begin with schematic capture. So at this point, it's sort of assumed that you've already kind of gone through your basic design, you know what your circuit is, and you place your schematic into the layout tool. All right, so you'll do that in OrCAD. What you then do is you get that schematic ready for layout. So Chandan will walk you through that process, basically how you attach package symbols, specifically what we call footprints. In other words, how we actually go about putting in the specific ways in which the chip itself or the component itself is laid out. So there's some basic things sort of mechanically that we need to get you introduced to understand this piece. And then creating a net list, which is an important element of the manufacturing process. This net list basically creates for us a list of all the nodes in the circuit and tells us where all the nodes are connected. Then he basically goes through setting up the PCB design environment, essentially creating some basic standards that he's going to use. So things like what basic line widths should be, what the vias are going to be. We're going to talk a lot more about this later on in the semester. We're just getting introduced to constraints. Then you're going to go through the process of actually laying out the circuit and placing the components. And so I guess it's really two things. One is you're placing the components, and two, you're then routing, which means that what you're doing is you're routing the nets. You're basically connecting the individual components with various traces, we call them. Then you're kind of going through your last steps to kind of prepare for manufacturing. So getting your what's called your silkscreen ready. So we'll talk about what that is. Then basically you're going to generate the files that are used to actually create this. And
The point over here, prepare for manufacture and generating your artwork or Gerber files or Gerber files. Okay, these are the files which you are going to send to the foundry, the manufacturing house. Okay, according to those files your PCB design will be fabricated. Then second last point is generating documentation. We do have a complete unit dedicated for the documentation part, and it is very important because that is the part where your technology transfer happens. So even if the person is not working with the company, the designs, the schematic, the calculations stays with the company, the IP stays with the company. Okay, so these are the important steps in the design process. We will go with the next part of the video. What is a netlist? Okay, whenever we have a schematic, if you consider an example of multisim, we always talk about a netlist. Netlist is nothing but the description of nodes in the electrical circuit and components attached in between the nodes. Okay, so over here we have battery, we have register and LED. And if you think about the nodes, the positive terminal is connected to one terminal of the resistor, so this is node 1. This terminal of the resistor is connected with the terminal anode terminal of the LED. So this is node 2. Okay. And we do have another node over here and another node over here, which may be connected to the chassis of the circuit or the ground plane, something like that. So we do have different nodes and description, their description. It is called as the netlist. Okay. Let us go with the basic structure of the PCB.
All right, so when we get to the PCB itself, the printed circuit board, just to introduce some basic concepts, right? So the board itself is made up of a couple of different layers. What I'm showing here is a basic 2-layer board. The critical layers you have are the copper layers. These are where the traces are that actually are the wires within the circuit, right, that are connecting the different components in the circuit. In this 2-layer board, then I have another one here on the bottom layer. So we'll refer to this as the top copper layer. Very often we just say the top layer, and then the bottom copper layer, or just the bottom layer. Between those is a dielectric material, which is essentially fiberglass, sometimes called the substrate. That material is referred to, that fiberglass material is referred to as FR4. And FR4 is, as I said, a particular type of fiberglass, has a particular dielectric set of dielectric properties and such that can be looked up. So typically, if you look at a basic board, what you have is copper on the top and on the bottom of one of those pieces of FR4 substrate. Now, in addition, what most boards also have is this sort of layer on top of that copper. It's on top, both on the bottom and on the top, called solder mask. We'll take a look at that in a second, but what solder mask is basically a layer of insulation that sits on top of the copper so that things won't touch each other. And then very often what you do is you have a layer of silkscreen on top. The silkscreen is basically text that allows us to identify what the components are. So just as a basic example of what we might have, let's say if we had a multi-layer board, which is eventually what you guys will get to, is you basically have a sandwich of these individual boards like this. So what I have here is I have copper and then some FR4, and then I have a layer of copper. And then I have another one down here with copper, FR4, and copper, and in between those I have a material called prepreg, which is a cheaper material, which helps the individual elements to adhere. All right, so in this particular case, I have a 4-layer board, and we'll see, that's pretty common, and most likely what most of you will ultimately develop when you get into Lab 3, where you need to use more than 2 layers. Just so you have an idea, if you're looking at a motherboard in a computer or something of that level of complexity, you might have something upwards of, say, 16 layers. And it might be a pretty complicated design. Most designs, are somewhere between 2 and 6 layers. All right, now I used a couple of terms there. I wanted to just kind of show these things. Some of you, or hopefully all of you, have seen a PCB at some point. The solder mask here is that green layer of material. And if I look carefully at the board, what I can see, these things here are called pads. All right, whenever I have exposed copper like this, it has that silvery look. That's a pad, and that's something to which I can solder. And so in this particular case, I've got 2 types of pads. I have these sort of annular rings, which are around what I call a plated through hole. So a hole that's been drilled through the board and is plated with copper all the way through the board. Those are the sorts of things that we typically solder to. Now there's another type of through hole that we don't solder to. That's called a via. All right, and that's this is a via right here. What that via is doing is it's connecting one layer to another. So it's connecting a wire on one layer to another layer. If I look carefully at this board, what I can see is I have these sort of, I don't know, lighter green areas, I guess, and then these kind of darker green areas. Where I have these lighter areas, that's basically where there's copper sitting on top of that FR4 substrate. So here I can see I've got a big copper area, right? This is what is sometimes called a copper pore, where copper is effectively in a large plane All right, so we'll use that terminology, a copper pour. These other sort of skinnier areas right here, these are copper traces. So essentially what's been done is the silk screen has been sat on top of the top layer. And so wherever it crosses over copper, you get this sort of lighter color. These darker areas, basically, that's just open board. Those are for what we call through-hole components. I also have pads that are sitting right here. Lab, you're going to deal mostly with surface mount components in your design. Although later on, we're going to switch over more to the boards that you're actually going to manufacture. And in those particular cases, we'll deal with through-hole components.
So it is important to have vias and traces which are running throughout your PCB. Vias connect those traces. Vias may be in between the layers or in between the top and the bottom layer. Okay, so we have to take care of the vias because those will act like what I will say that waveguide. If we are working at megahertz frequency for that particular via, then that via, due to its cylindrical nature, will act as a waveguide for megahertz frequencies. Okay, so we have to take care of lots of issues over here. We usually make the copper floor or copper plane in larger area terms for the ground and the power to have more effective distribution of heat. Okay. The white markings and the words you look at here on the PCB, it is called as silk screen, where we print the names, the information of the PCB. Okay. So whenever we are going to design PCB, we have to consider lots of things like we have seen today. One example which takes care of the EMI issues and few of the design processes through which we have to go while fabricating the PCB. That's all for today's session. We will gather yesterday's information and today's information all together, and we will summarize them for our unit number 4 in a more structured way. Okay, and we will see how these videos helped us to complete the syllabus of unit number 4, and probably tomorrow we will finish unit number 4. Okay, that's all for today's session. Everyone take care. Bye bye.
Bye bye.